Welcome back to this lecture series on pulse width modulation for power electronic converters. So, today we will be looking at, this is the 13th lecture, and we will be looking at selective harmonic elimination. The last few lectures we have been focusing on low frequency pulse width modulation, that is we have a voltage source inverter like this. This inverter, it switches at certain frequency. So, at what frequency, that is by and large decided by the power rating and the nature of the devices that you have here. So, sometimes these devices can switch at very high frequencies. If you consider certain MOSFET inverters, they might probably be able to switch at several hundreds of kilohertz. So, it depends on what the device is. And in case of IGBT inverters, you will find that many times this can probably switch at the order of kilohertz. I mean, typically IGBT switch up to 20 kilohertz. So, you may find about 5, 10 or 20 kilohertz kind of this thing. These all depends on the choice of device depends on the application, the rating, etc. So, you come to still higher power converters, you will use you will switch the devices at lower frequencies. As the rating goes on increasing, the switching frequency is low, and at very high power levels you will tend to switch at fairly low frequencies. That is because every time the switch turns on or turns off, every time it turns on turns off, there is certain amount of energy that is lost. So, the total switching loss is the product of this energy loss per switching cycle multiplied by the number of switching cycles per second. Therefore, to keep the switching loss low within permissible limits, if your energy loss is very high, you have to keep your switching frequency low. And so, therefore, at high power levels, when the voltages and the currents that are being switched are very high, you tend to switch at very low frequencies. And so, we have been looking at how to modulate inverters at low frequencies. That is what we have been looking at over the last couple of lectures. How do we go about doing it? So, one of those methods that we have come upon now is selective harmonic elimination. So, here we are looking at, I have indicated it as IGBT inverters. As I mentioned, this could be any kind, but at a very higher power levels, it could certainly be high voltage and high power IGBTs. So, there are IGBTs which can handle voltages of the order of 3000 volts or so, and the currents are also going into 1000 amperes and so on. It is possible these days to realize IGBT inverters up to power levels of even a few megawatts or so. So, when the power level is high, typically the switching frequency tends to be low. So, now it is we are even more interested in learning, even rather than it is the application where the low switching frequency is useful for high power drives. What we are interested in, low switching frequency gives us a nice opportunity to learn pulse width modulation. So, that is why we have been focusing on this 2 switching angle problem. That is, the pole voltage here has only 2 switching angles here, alpha 1 and alpha 2, excuse me, alpha 1 and alpha 2 that I have indicated here. The waveform is quarter wave symmetric. So, the next quarter is a mirror reflection of this. Then it is half wave symmetric. So, and then there are 3 phase symmetries. So, it is only 2 switching angles. You need at least 1 switching angle to control the fundamental voltage. Because you have 2 switching angles, it is possible for you to influence the harmonics to certain extent. So, that is what we are looking at now. How do you go about influencing the harmonics now? So, we looked at the fundamental voltage control. So, what we saw was the switching angle problem. You can look at this waveform as a point on this plane alpha 2 versus alpha 1, where alpha 1 is one of the switching angles and alpha 2 is the other switching angle. So, you see these points, how they go about. So, we saw that any point here, like those are indicated here, they are in any point there, is it represents a waveform of a particular value of alpha 1 and a particular value of alpha 2. And this red curve is the 0 fundamental voltage curve. So, along that, if you choose alpha 1 and alpha 2, the fundamental voltage is 0. So, below that, that is as indicated by this green point here, it has some fundamental voltage, and if you look at blue, that also has some fundamental voltage, and these two have a phase reversal between these two. So, here the phase will be something, here the phase will be on a 180 degrees later. So, normally we will focus on this range. If you go beyond this, the phase is going to be reversed, it is going to be 180 degrees different from what we would want, right. So, you can look at all this, there are several of these curves now. So, here that V1 is equal to 0 curve is shown by this blue line, then you have like 0.2 is indicated here. As you go about increasing V 1 like this, your curves keep shifting like this, and finally this curve is your V 1 is equal to 1 per unit, that is square wave. In square wave, alpha 1 is equal to alpha 2, the two switching angles come together. So, that is basically there is no switching in any quarter, there are only switchings at 0 and 180 degrees here. That is, you go back to this waveform, there is only switching at 0, these two come together. So, there will be only other switching at 180 degree. So, a phase will switch only twice in a cycle. So, it is in the square wave operation, the whole pole voltage will be a square wave now. So, this is how the fundamental voltage goes on, and we also saw that you can think of a PWM technique as a locus of a point which starts from one point on this curve V 1 is equal to 0 and moves towards V 1 is equal to 1 or some V 1 is equal to maximum that we would want. So, we are now looking at specifically the problem of eliminating a particular harmonic voltage. Since we have two switching angles, there are two independent variables available, we can try to control the fundamental voltage and also try to eliminate one of the harmonics. In this case, we will try and eliminate the fifth harmonic. As I mentioned in the last lecture, fifth harmonic is what is the lowest harmonic, and that is what faces the lowest amount of leakage reactance among the harmonic voltages. Seventh harmonic will have will face much higher than that. The harmonic voltages, they see the machine as its leakage inductance. So, the reactance seen by the fifth harmonic voltage is 5 omega L, and the reactance seen by the seventh harmonic is 7 omega L. So, the reactance seen by something like the 31st harmonic is 31 omega L. So, the higher harmonics see a greater amount of harmonic reactance, and therefore, their corresponding harmonic current amplitudes are going to be lower. So, the one that is going to cause maximum problem is the lowest harmonic content, that is fifth. We will not have third harmonic here, because that will get cancelled. Okay. So, we have seen that you have two equations and two unknowns, and therefore, you can go about solving them, and you have to solve them, you can't solve straight away, you need a numerical iterative procedure, and to solve that you need a starting solution. If you are able to make a good initial guess, it can converge much faster, and sometimes it may lead to a particular solution, sometimes it may lead to another solution depending on what is your starting guess. So, sometimes there could be multiple solutions as indicated here, but sometimes the solution could be unique, and sometimes there may not be any solution at all. So, what you generally do is you just try, well, if there is no solution after a long time, you kind of give up, or you change your initial guess and try. So, what we are trying to see is try to understand these better. When does this harmonic elimination problem, when is it likely to have no solution? When is it likely to have fewer number of solutions or just one solution? When is it likely to have more number of solutions? We want to get a grasp over these things, and that is why we are going in for a graphical approach first, because it is possible to look at this graphically since we have only two switching angles here to develop some understanding and some insight, as I was mentioning earlier. So, if I want to do that, I want to plot, let us say V phi is equal to 0 contour. So, 1 minus 2 cos phi alpha 1 plus 2 cos phi alpha 2 is 0, that is the equation. Basically, I want to plot this. So, what do I do? Simple, go on substituting different values of alpha 1, and find out what the corresponding values of alpha 2 are. So, here I have started with alpha 1 is equal to 0. Why? Very simple thing. The alpha 1 itself can vary from 0 to 90 degrees, So, I start from 0. So, I have cos phi alpha 2 is 0.5 and corresponding alpha 2 I am getting is 12 degrees. So, let me just choose some ink here. So, for alpha 1 is 0, I am getting alpha corresponding alpha 2 is 12 degrees. So, I know one point, then I am going into the next point. What is this? 6 degrees. I can choose 1 degree, I can choose 2 degrees, whatever. I am trying to keep it a little higher. 6 degrees, why 6 degrees? You see I have 5 alpha 1. So, 5 alpha 1 meaning 5 into 6 is 30 degrees. It is a little easier for us to handle such numbers now. So, I choose 6 degrees now. So, I am getting corresponding alpha 2 as 13.7 degrees, there is some small increase there. Then I go to 12 degrees, add another 6 degrees more, and I get a corresponding alpha 2 that is 18 degrees. So, my alpha 1 is increasing considerably in big steps of 6 degrees. Here I see that the first step is increased by about 1.7. The next step is more than that, it has increased by something like 4.3 degrees now. Alright, I go further up, say alpha 1 is equal to 18 degrees. I get my solution as alpha 2 equals 24 degrees. So, if alpha 2 is 24, so 18 cos phi alpha 1 is basically cos 90, that is 0, and therefore, you are going to get as cos phi alpha 2 as minus 0.5. So, phi alpha 2 is 120 and alpha 2 is 24 degrees. So, you get this point now. So, I have one more point. Similarly, you go about getting 24 degrees, you get minus 1 and phi alpha 2 is 180 degrees and alpha 2 is 36 degrees. Then, if I substitute 30 degrees, I get cos phi alpha 1 is equal to minus 1.36x, which is beyond that. Any cosine function can have values only ranging between minus 1 and plus 1, and this is lower than minus 1. So, there is no solution here. So, for any value of alpha 1, there is no corresponding value of alpha 2 that is available here now. So, what do we do? Let us just start plotting this. So, if we plot this, you started with alpha 1 is 0 and alpha 2 equals 12 degrees. So, let me choose alpha 1 is 12 and alpha 2 is alpha 1 is 0 and alpha 2 is 12. So, so this is my point, that is the point that I have indicated here now. The next point I have considered is 6 degrees and 13.7 degrees. So, 6 is here and 13.7 is slightly above that, You see that I have formed a grid once in every 6 degrees, which is basically 30 degrees divided by 5. It is convenient to draw this. So, I have just taken a grid like this. Well, you can do it with any grid, or you can do it on a graph sheet, you can do it wherever you want. There is a tendency on the part of students generally to plot all this using a computer package and plot them, that is very efficient in terms of time. But I suspect that you might miss out on certain things. So, I would generally recommend students to plot this, at least when you are doing it for the very first time or so, to plot it manually, so that you understand certain things. You will understand the trends of the curves and some insight which is difficult to even describe or whatever, you will get that. So, I would generally recommend students that you plot it first. So, you will give you a good experience of good knowledge of what the nature of variation is. So, at alpha 1 is equal to 6 degrees, you get something like 12 degrees now. So, if I go to 12 degrees, it is 18. So, 12 it is 18 like this. I go to the next point. So, it is 18 is 24, alpha 1 is 18, then this is 24. Okay. Then I am looking at alpha 1 is 24, alpha 1 is 24, it is 180 degrees. I am sorry, 24, phi alpha 2 is 180, alpha 2 is 36 degrees, right. So, I am getting here. So, this is what we have come. Let me join this together. So, here it is a slope, it looks like 0 slope. You can actually verify that the slope is 0 when you are close to alpha 1 is equal to 0 degrees, and you do this now. So, this is how the curve is. And many a times, whenever I ask students to plot this V phi is equal to 0 contours, the curve stops here. But is this complete? No. There are more solutions available for the equation V phi is equal to 0. More solutions within the region of our interest. What is the region of our interest? We are looking at only 0 less than or equal to alpha 1, which is less than or equal to alpha 2, which is again less than or equal to 90 degree. We are looking at this upper triangle that I show here in this figure. So, within that there are more. So, why have I missed out? One thing is very simple. When I say alpha 1 is equal to 0 and cos phi alpha 2 is 0.5, it is not phi alpha 2 is 60, it is only one of the principal solutions there. There are also other solutions here. Phi alpha 2 is equal to 60 is not the only solution. Phi alpha 2 is equal to 300 is also a solution. So, phi alpha 2 is equal to 420 is also a solution. I have mentioned this before, but I just want to state this again. So, you get these things here. So, when you say phi alpha 2 is instead of 60, it is 300 degrees. So, if it is 300, 300 by 5 is 60 degrees. So, at this point you also have one more point like this. In fact, if you consider all of them, there is not just 300, it is also 420 degrees is also solution. 5 alpha 2 is equal to 420. So, that is 72 degrees. So, if you look at these solutions, and the next solution might really go beyond that, the next solution may really go beyond the range of our interest now. So, let us stop there. So, if you really look at this, if you consider all those points, you will get these points also, you will get these points also here, and what you will have is really a curve going around like this. These two will be symmetric about this line, and similarly you will have another curve which is just going up the same way. Like this. This would be basically, excuse me. So, this curve that I am showing, this curve you reflect it, you are going to get this curve, and this curve is basically shifted up to this curve. This is something that we plotted in the previous lecture too. So, but this is not all, you need to go further from here. So, this is what we you get here now. So, there are multiple solutions here. So, it's you first let us look at what those angles are. So, there are curves, we have only looked at the range alpha 1 is 0 to 24 degrees, and at 30 degrees we did not get a solution. So, we stopped there, but maybe for higher values you will get solutions, is that right? Okay. So, what values will I get solution now? Let us say for alpha 1 is equal to 0, I got some solution which is alpha 2 is equal to 12 degrees for this fifth harmonic elimination, or V phi is equal to 0 contour. Now, if I increase, it has the equation as a cos phi alpha 1 term. So, the cos phi alpha 1 value is not going to change if I am going to change my phi alpha 1 by 360 degrees or change my alpha 1 by 72 degrees. So, if I go here by 72 degrees, if I can go here to another 72 degrees, let me go back to the previous one to look at that, or maybe you can even look at a fresh plot, or we will come to this here. Okay. Excuse me. Yeah. So, if you have a point here, 72 degrees later you will also have a point here. So, 72 degrees you will have a point here. Why? Alpha 1 is changed by 72 degrees. So, phi alpha 1 is changed by 360 degrees. So, cos phi alpha 1's value is unchanged now. So, the same way you should remember actually that this curve has a negative side also. For negative values of alpha 1 also, you have this curve going symmetrically on the other side, you have it symmetrically on the other side. So, this will also shift up here. So, what is going to happen is, if this is alpha 1 and here if you have a point, this point is about 24 degrees. So, this will also shift here at 24, meaning 24 plus 72 is 96 degrees, which goes a little outside here now. So, if I take this 0 instead of 0, I mean I have got a point here, 0 next to 6 degrees. So, 6 plus 72 is 78 degrees here. So, I will get a curve like this, I will get this curve going like this, another point like this. So, I may get certain points going around. So, I will actually have another curve like this, I will have one other curve like this. So, which is basically the first curve shifted by 72 degrees. Now, similarly this curve that you see in the top is again this bottom curve shifted up by 72 degrees. So, if alpha 2 is changed by 72 degrees, phi alpha 2 changes by 360 degrees and cos phi alpha 2's value is unchanged. So, you can shift this entire curve. So, it is basically it is part of another curve there, this curve has been shifted up. So, you can shift it by right or left by 72 degrees, or you can also shift it to top or bottom, you will get the same curve. Once you get one V phi is equal to 0 contour, you can get as many of them as you would want now. In fact, if you shift it further, this one to the right or this one up, you are in fact going to get one more curve like this. And if you see, certain curves are in this and our region of interest. Let me just change the ink color, or yeah. So, this part of the curve is in our region of interest, what I am drawing with the green ink now. Again this part of the curve is also in our region of interest. So, let me indicate with a different color V1 is equal to 0 contour. The V1 is equal to 0 contour we are looking at goes something like this. So, these two curves are solutions, what have been indicated here by the green lines. This curve and this curve are solutions here now. So, one other way is to look at the slopes. If you look at the slopes, what is that? 1 minus 2 cos phi alpha 1 plus 2 cos phi alpha 2 is 0. If you want to get the slope of V phi is equal to 0 contour, you differentiate this equation, both sides of the equation with respect to alpha 1. So, you will end up getting this is 10 sin phi alpha 1 minus 10 sin phi alpha 2 is times d alpha 2 by d alpha 1 is 0. Then you have d alpha 2 by d alpha 1 and take the other terms to the other side, you get an expression d alpha 2 by d alpha 1 is equal to sin phi alpha 1 by sin phi alpha 2. So, this is how the nature of the slope is. So, sometimes your slope is 0 whenever the numerator is 0. When is the numerator 0? The numerator is 0 whenever sin phi alpha 1 is 0 and the denominator is 0 whenever sin phi alpha 2 is 0, that is the slope is infinity now. So, you can see that there are points at alpha 1 is equal to 0, the slope is 0. Again when alpha 1 is equal to 36 degrees, phi alpha 1 is 180 and sin 180 is 0. So, at alpha 1 is equal to 0, at alpha 1 is equal to 36, at alpha 1 is equal to 72 etcetera, it is possible to see one such point. So, you say alpha 1 is equal to 0 and you look at what are the corresponding values of alpha 2. If you take alpha 1 is equal to 0, the other corresponding values of alpha 2 could be 12 degrees, 60 degrees, 72 degrees etcetera. In every one of these point, at every one of this point, the slope of V phi is equal to 0 contour is 0. It is 0 here, the slope is 0 here, the slope is also 0 here. So, again infinity, when sin phi alpha 2 is 0, it is infinity. Sin phi alpha 2 is 0 when alpha 2 is equal to 36 degrees. This is alpha 2 is 36 degrees. So, when alpha 2 is equal to 36 degrees, your alpha 1 sorry it is 24 alpha 2 is 36 degrees, the corresponding alpha 1 is 24 degrees. So, these points you can very quickly identify the points where this curve has 0 slope and infinite slope. It has 0 slope and infinite slope and you can also plot them very quickly. If you start from here, let us say I choose some ink, there is something centered at 36 degrees. This 36 degrees is basically 180 divided by 5. Let me write 180 divided by 5, that is this point, and from here it is 24 degrees away. So, this is a point where you have 0 slope, again this is a point where you have 0 slope. So, if you look at other point where the slope is infinity, you will find that the slope has infinity here, and similarly on the other side, maybe it is good if I erase this, let me erase this point. So, there is another one on this side which is basically minus 24 degrees. So, you can very quickly come up with this contour. It looks like a circle, it is not exactly circle, it is more curved in this sides, I mean it is, and it is kind of straight line towards the center now. So, what you really have is a curve which is going like this now. So, you can also identify the next set of points. Similarly, at 72 degrees you have this, and again there is another point here, you this is plus 24, 72 plus 24 is 96 degrees. So, at 96 degrees you will have again infinite slope. So, you get this like that. So, you can identify the points where the slope is 0 and infinity, and you can go about getting these curves much more quickly. This is what I have been trying to put across. So, you now these three cover practically our region of our interest. There is no fourth curve that is possible within our region of interest now. Our region of interest being alpha 1 greater than 0 and alpha 1 should be less than or equal to alpha 2, and again alpha 2 has to be less than or equal to 90 degree, the upper triangle that is shown here. So, there are not only these three curves, And once again, as I mentioned a little earlier, you take V 1 is equal to 0 and you are looking at only one phase, you are not looking at the other version like V 1 is equal to 0.5 or minus 0.5. So, your bounds are only within this. So, you have these two solutions available now. So, this gives us a clearer picture of what we are trying to do. So, let us see what are those two curves we are getting. Let me just sketch this part. This is I am drawing it very roughly, okay. I am not doing very this thing. So, let me say what are the two curves that we got? One curve started from here, one curve was like this, and the other part of the curve is like this. Like this. So, we looked at this question about the solution for fifth harmonic. Before that, let us start looking at the fundamental voltage. How does the fundamental voltage vary along this now? Let me choose a different ink color. What is the fundamental voltage here? This fundamental voltage is 0. V 1 is equal to 0 along this line. Is that right? So, it is also 0 here. V 1 is 0 here too. And as we move along this, V 1 actually goes on increasing. And you see here V 1 will be something like 0.95 when you come to this point. V 1 will be something like 0.95. Similarly, along this point if you start and you go moving here, at this point V 1 will be something like 0.8. So, this is how it varies. As you move along this curve, you are coming within this area. So, your V 1 is actually increasing little and you are going all the way up to V 1 is equal to 0.95 and here you are going up to 0.8 now. So, what does it say? If this V 1 is equal to 0.95 is the highest value along of fundamental voltage along this particular curve, and again this V 1 is equal to 0.8 is the highest value of the fundamental voltage along this particular curve, the other red curve that I have been showing here. So, in this case the fundamental voltage varies anywhere is between 0 and 0.8 and along this curve it is anywhere between 0 and 0.95. So, can there be no solution to the fundamental equation? That was a question that we were asking. Yes, fifth harmonic elimination, will it have a no solution? Of course. If you have a fundamental voltage that is greater than 0.95, I mean this, please remember that this 0.95 is it is not a very precise number, okay, I am giving it, yeah. You can just work out what that number exactly is. It is after all alpha 1 is 0 and alpha 2 is equal to 12 degrees now. So, if you take anything above that, there is going to be no solution for your fifth harmonic elimination. Can I solve fifth harmonic elimination, for example, when I want V 1 is equal to 1 per unit? If I want V 1 is equal to 1 per unit, it is a square wave and there is no switching. So, you cannot eliminate any harmonic. So, fifth harmonic elimination is not possible for V 1 is equal to 1, it will not be possible for some values very close to 1. How close is that is the question that you are coming to determine, I mean that is what we have come to determine now. As far as the fifth harmonic elimination is concerned, something like 0.95 is what the number is. If you are really above this, if you are like 0.98 or 0.99, there is going to be no solution for your fifth harmonic elimination problem now. Then how about, are there going to be multiple solutions? Yes. How? When? If you are looking at a fundamental voltage, if you are looking at some fundamental voltage, let me once again draw it with let us say blue ink, looking at something like 0.4. So, I am going to get a curve which is like this. This curve may be like V 1 is equal to 0.4 or whatever 0.3 intersects this V 5 is equal to 0 contour and it also intersects the other V 5 is equal to 0 contour. So, it has two different solutions now. Up to what range? Up to 0 to 0.8, there are two different solutions possible, because any V 1 is equal to 0, V 1 is equal to constant contour where V 1 is anywhere between 0 and 0.8 will intersect both this curve as well as that curve. Whereas, if you choose something like V 1 is equal to 0.93 or so, it may intersect only this curve but it may not intersect the other curve at the top right corner. So, this has only one solution. So, we can say the solutions for fifth harmonic elimination problem in the range of V 1, something like 0 to V 1 to 0.8. In this range, you have two solutions are possible. You have two solutions possible. So, if you look at the range 0.8 to something like 0.95 or 0.96, we will have only one solution is possible. And if you are talking of V 1 greater than 0.95, there is no solution. So, whenever you are very close to the sixth step, there is a chance that there may be no solutions. That is something that we have to remember. And again, it is not necessary that as you go down to lower and lower ranges, the number of solutions should go on increasing. At lower ranges, the number of solutions is certainly higher. That is what we can really say from here now. So, what you would generally do is to solve fifth harmonic problem. This is a graphical approach, and this is meant only for two switching angles. For anything, you can always solve those equations. It is two equations in our case when there are two switching angles. When there are three switching angles, there are going to be three equations, and you have to solve that iteratively. Now, it depends on what you want. Let us say you have something like V 1 is equal to 0.8, something like V 1 is equal to 0.8 or so. So, let us say this is the curve that you have, this is the fundamental voltage curve you may have. So, now you have the other V 5 is equal to 0, this is like this, and here it is like this. So, it depends on where you are starting from and how the convergence happens with your solution. Let us say you might have started, it depends on your initial guess and the numerical procedure. So, depending on whichever starting point, sometimes you may end up with this point as one solution, and otherwise you may end up at that point as the solution. So, it depends on your initial guess also. So, it is possible that when the problem is very complex, still certain solutions have not been found. You really do not know, you can go on doing many things. It depends on your initial guess here. So, depending on that, you are going to get solutions now. So, sometimes if your initial guess is very bad, it will take more time to come up. If your initial guess is better, you may be able to solve this problem much more quickly. So, when you have an idea of the solutions, then your initial guess could be better. So, that is one of the reasons why we are trying to do all this. So, with this kind of an approach, you will see that you will start slowly learning how to make a good initial guess. So, that is one of the intentions here now. So, it depends on your initial guess, and also if there is some other V 1, let us say you take another value of V 1, this could be another value of V 1. So, you may want to solve for V 1 is equal to 0.3 and V 5 is equal to 0. So, depending on your initial guess, your iterative procedure will bring you to either one solution which is here or the other solution that is there. So, if it is more than 0.95, you may not get any solution at all. So, this is how you get it for the fifth harmonic elimination problem now. So, let us look at how do you eliminate a seventh harmonic. Instead of fifth harmonic, for some reasons you might want to choose a seventh harmonic eliminate. See, sometimes it is possible that you can use passive filters, tuned passive filters, which can selectively bypass or filter out certain harmonics. So, maybe for fifth harmonic you might have some filtering. So, you might want to filter out the seventh harmonic. So, let us say you want to eliminate seventh harmonic. So, what do you want to do? You have the equation slightly different. So, V 1 is 1 minus 2 cos alpha, it is the same thing, and instead of V 5 is equal to 0, you now have V 7 is equal to 0. It is the same old story, two equations, two unknowns. You will have to use a numerical procedure to solve this, and you need a good initial guess. And once again you might have multiple solutions or a single solution or no solution at all. And once again it is possible to solve it graphically, because we are still with two switching angles only. So, let us just try doing that. So, if you follow a very similar kind of an approach that we followed earlier, that is now we can calculate and plot V 7 is equal to 0 contour. So, how do we do that? The same way you take 1 minus 2 cos 7 alpha 1 plus 2 cos 7 alpha 2 0, and fill feed values of alpha 1 and try to find out what those values of corresponding values of alpha 2 are. So, if you see I have taken alpha 1 is 0 and the next value I am trying to take is alpha 1 is 30 by 7. It is easier that way because 7 alpha 1 will then be 30 degrees and I am taking the next value 60 by 7. So, 7 alpha 1 will be 60 degrees. So, it is kind of easy to do my calculations and all that. So, we are just taking some numbers like that. So, 30 by 7 is essentially something like 4.3 and 60 by 7 is something like 8.6 or 8.7. Again 90 by 7 is something close to 13, little less than 13 degrees. So, the corresponding solutions are all given here now. So, let us look at what those solutions are. So, at alpha 1 is 0, the corresponding solution is alpha 2 is 8.57. It is the same procedure. Now, alpha 2 is 9.79. So, alpha 1 is 60 by 7. As I said, it is a little more than 8 degrees, something like 8.6 or so. So, the corresponding alpha 2 is 12.86 now. Again, when you have alpha 1 is 90 by 7, which is a little less than 13 degrees, your alpha 2 is 17.14. So, you go for more values. So, take 120 by 7. So, for this your corresponding value of alpha 2 is 25.71. Then you have 150 by 7 for which you go and it says it is beyond solutions. So, for certain values of alpha 1 you may not have no solutions at all, it is really like this now. Okay, so, let us look at just plotting this. So, first is 0 and alpha 2 is 8.57 degrees. So, alpha 1 is 0 and alpha 2 is 8.57 degrees. Basically, more than that what I can say is 7 alpha 2 is 60, alpha 2 is 60 by 7. So, what I have done here is I have divided every 30 degree into 7 grids. I have just made a suitable kind of a grid here. So, everything is 30 by 7 and you get, so one grid here is 30 by 7. So, 60 by 7 is here, my point is somewhere here. So, if I go next, what is the next point? Alpha 1 is 30 by 7, my corresponding alpha 2 is something like 9.79 degrees. It is alpha 2 is some little more than that 9.79. You see the slope is very small, the slope is very small now, right. Then I go to the third point 60 by 7. So, here alpha 2 is 12.86 degrees or basically 7 alpha 2 is 90. So, the point is here 7 alpha. So, the point is here now. So, the curve is gradually going up as you can see. So, if I go to 90 by 7, 90 by 7 then which is roughly 13 degrees, alpha 2 is 17.4 degrees. Alpha 2 is 17.4. So, it is somewhere like that. So, then you come to 120 by 7, you have alpha 2 is 25.71 degrees. So, 25.71 is something like here. So, this is the curve that you have, this is the curve that you have and this is just one of the solutions. So, if you go the other side, you will have 2, 3, 4, 1, 2, 3, 4. So, you have this coming around and going back to this. This is a V 7 is equal to 0 contour and of course, you have this curve going to the left also, this going to the left also. This curve is in fact symmetric about this point, it is symmetric about that, it is not a circle, it does not have a radial symmetry, but every quadrant here is symmetric. So, if you draw one quadrant, you can get the other quadrants by reflecting them. So, every quadrant is symmetric about that. So, you can get this now. So, again what as we have understood earlier, if this is a point, let us say let me go back to the same color that I chose earlier, right. Okay. So, if I shift alpha 1 now by 360 by 7, 360 by 7 is something like 52 degrees, it is a little less than 51.4 degrees or so. If I shift it by 51.4 degrees, what happens is correspondingly 7 alpha 1 increases by 360 degrees and cos 7 alpha 1 is unchanged. So, all these curves can really be shifted. So, it is somewhere around 51 degrees you will get that, which is should I say here. So, you may get a curve which is going around. So, this is 25.7. So, this will further get shifted here. So, what you will have is you may have some curve which is like this, some kind of curve you will get like this, which is exactly you can shift it to the right by 100 degree. This curve is not within our region of interest, because it comes in a range where alpha 1 is greater than alpha 2, which is not possible for us now. Whereas, if you shift this curve up, you will get a corresponding curve there, right. So, what will that curve be? You will get in fact 3, 4, 5, 6. You will actually get another curve which comes from the other side. So, you will have multiple curves coming up now. So, this curve, if you really see, it will get shifted up. Let me just blue line. So, one of this curve, if I shift up, it will actually be like here. This curve will actually go through this point. One thing I want to tell you is, all these curves will go through one particular point, that is the green point I am indicating here. Why? What is that point? That point is 60, 90. All this V phi is equal to 0 contour also went through that point, the curve was different. If I redraw the curve here, that curve went through like this, something like that, whereas this curve is going around like this now. So, why? All these curves will go through that, because 60, 90 corresponds to a third harmonic square wave. So, a third harmonic square wave contains no harmonics, neither fifth harmonic nor seventh harmonic, neither 11th harmonic nor 13th harmonic. So, any V n will be equal to 0, any where n is any non-triplet harmonic order. So, at this point you have V phi is equal to 0, V 7 is equal to 0, V 11 is equal to 0, V 13 is equal to 0, and all of them will be equal to 0. So, many a times that is a good starting point when you want to solve for numerical solutions, because the harmonic equations are straight away satisfied at that particular point now. So, you can also shift this curve a little this side and you will come up with yet another curve which passes through 60 degrees now. So, what you will get is, I will go back to the same black color. Yeah. So, I will have another curve like this, may have another curve going around like this now. So, this is yet another curve now. So, I now find that there are a few different curves. Let me choose a different color to highlight which of these curves fall within my region of interest. This curve falls within my region of interest. This is basically one half of a complete curve, and this again part of this curve falls within my region of interest. Part of this curve falls within my region of interest now. So, at this point you have some value of V 1, at this point you will have some value of V 1. What is that point actually? You can just find it out. It is for alpha 1 is equal to 0 and the corresponding value of alpha 2 that we got, that is alpha 1 is equal to 0, 7 alpha 2 is equal to 60, or 7 alpha 2 can be 300 degrees. So, what you have is alpha 2 is 300 by 7. So, that point is actually alpha 2 is equal to 300 by 7. So, at this point, so if you take this point, the fundamental voltage is low, and let me use an arrow here. So, at this point the fundamental voltage is low. As you go around moving this curve, as you go on moving around this curve, your fundamental voltage will increase and it will come to some other value, excuse me, it will come to some other value. So, there is a range over which the fundamental voltage varies along this curve, and that range starts from somewhere higher than V 1 is equal to 0, right. Now, you take this curve. Now, this is V 1 is equal to 0, the blue line is V 1 is equal to 0, excuse me, the blue line is V 1 is equal to 0. So, as you move from both the sides, so for something like V 1 is equal to 0.1, this curve itself offers two different solutions. Is that clear? Let me just use blue ink and draw another line. Now, let me say I have some other V 1 is equal to 0.1 or so. That V 1 is equal to 0.1 or so is going to intersect this particular green curve itself at two different points. So, this curve itself offers two different solutions, and there can be a set of values of V 1 for which you may have like this. It will intersect twice on this curve and once here. So, sometimes you may have two solutions and sometimes you may have three solutions, and when you go beyond this particular point for some higher value of V 1 which does not cut this intersect this green curve at all, but it intersects only here, you may have one solution. And finally, when your V 1 goes very close to the 6 step voltage, there can be 0 solutions. So, here what we find is at low voltages starting from V 1 is equal to 0 to some value, you will find two solutions. That value is basically the whatever is the fundamental voltage at this point, this curve. Yeah. So, from that fundamental voltage, let me just write down some value so that it is clear as to what we are trying to say. So, let me call this fundamental voltage as V A, and let me call this value which is tangential as V B, that is the line V B, fundamental voltage equal to V B is tangential to this green curve now, and then you may have some voltage V C. So, between 0 and V A, you may have two solutions, and for the range V A to V B you may have three solutions, because this will intersect twice in this curve and it will intersect once in this left bottom curve. And if you have gone beyond V B and all the way up to V C, your V 1 is equal to constant curve will only intersect this particular green curve, that is the left bottom curve, and it will not intersect the right top curve. So, you may get only one, and if your fundamental voltage is even greater than V C, you will have no solution. This is greater than V C, you may have no solution. So, what these values of V A, V B and V C are, I would leave them to you as exercises to find out. They are reasonably simple exercises, and the interesting point is, at V B you will find that the curve, the constant voltage curve V 1 is equal to V B and V 7 is equal to 0 will be tangential to one another. Okay. So, that is the condition you must use to come up with what the exact value of V B is. So, the 7th harmonic solution problem, if you look at it, it offers a lot of issues, like there are multiple solutions and there are no solutions, etc. And it is also good if you look at the what is the V 7 is equal to 0 contour slope is going to be. So, it is the same thing, 1 minus 2 cos 7 alpha 1 plus 2 cos 7 alpha 2 equals 0, instead of 5 it is 7 in this equation now. If you want to find the slope, what you need to do is differentiate both sides of this equation with respect to alpha 1. So, you are going to get something like 10 times, or I am sorry, it is 14 times. So, 14 times sine of 7 alpha 1 minus 14 times sine of 7 alpha 2 times d alpha 2 by d alpha 1 is 0. So, once again you will have d alpha 2 by d alpha 1 is equal to sine of 7 alpha 1 by sine of 7 alpha 2. This is true for any V 7 is equal to 0 contour. So, you can see that it is very similar. What was it in case of V 5 is equal to 0 contour? The slope of the V 5 is equal to 0 contour we found was sin phi alpha 1 by sin phi alpha 2. Now, it is sin 7 alpha 1 by sin 7 alpha 2. So, you can very easily generalize. If you replace this as n alpha 1 n alpha 2 for any nth harmonic, you will find that the curve is d alpha 2 upon d alpha 1 is equal to sin of n alpha 1 divided by sin of n alpha 2. This is for any particular V n is equal to 0. It can be V 11 is equal to 0 or V 13 is equal to 0 and whatever. So, this is how the slopes are for any V 7 is equal to 0 contour or any V n is equal to 0. and from this slope it is very easy for you to find out where these curves are going through zeros, I mean 0 slope and where it is infinite slope, and you can very easily come up with certain sketches that you really want to have here. So, these kind of sketches that we really saw, it is easier to come now. So, for example, if slope is 0, what we mean is, in this case we say sine of 7 alpha 1 is 0. Here we mean sine of 7 alpha 2 is 0. So, there are values of alpha 1 for which you get 0 slope, that is alpha 1 is 0. Then the next value is 7 alpha 1 is 180, or you have alpha 1 is 180 by 7, then 360 by 7, then 720, I am sorry 540 by 7. So, 540 by 7 and so on. So, for these various values of alpha 1, you find out the corresponding values of alpha 2, and at all those points you will find that this V 7 is equal to 0 contour has 0 slope. Similarly, you look at wherever the slope is infinity, the curve is vertical. So, sin 7 alpha 2 is 0. So, what you will have is so sin 7 alpha 2 is 0. So, same way this is satisfied whenever you have alpha 2 is whatever, alpha 2 can be 0 and alpha 2 is 180 by 7, alpha 2 is 360 by 7, 540 by 7 and so on. So, at these values of alpha 2, you plug in these values of alpha 2 in your V 7 is equal to 0 equation and find out the corresponding values of alpha 1. So, at these points alpha 1 comma alpha 2, you will find that its V 7 has infinite slope now, and if you are able to spot them, you get those curves. Basically, the contours are like this. All that we are trying to do here is, let me use a slightly different color to indicate that. So, you can very easily come up with these yellow points, you can very easily come up with these points, which are really the corners. So, once you have the 4 corners available, you know what the nature of curve is fairly quickly. So, this is about your infinity and things like this now. So, as I said that you can use that idea to plot it very quickly. So, you know that it is 0 slope here, and you know that it is infinite slope here, and you know that it is some 0 slope here. So, once you know that the nature of the curve is going to be something like this, and once you know that this is the other side of the curve. So, you can translate this curve, you can shift this by 360 by 7 degrees to the right, or 360 by 7 to the left, 360 degrees by 7 to the bottom or top, and you go about getting the other curves that you want to get now, which is what the burden of our argument has been, right. So, you can get the other curves that you want. Is it okay? So, you can very easily come up with these points once you have them now, at least roughly you can come up with what you want to say now. So, as I said about this 5th harmonic, please mean it is about 7th harmonic elimination problem. Here again you have, there are 2 solutions, and you can have 3 solutions in some other range, and you may have only 1 solution in some range, and you may have no solution in some other range. It is possible for you to find out what are these ranges and things like this now. So, when you solve them, what you are really trying to do is, though you may have a particular value of V 1. So, that may be a curve going like this, it may be a curve going like this, and you will have V 7 is equal to 0. So, that may be a curve like that. So, you are trying to find out this point of intersection by solving those 2 new equations iteratively. So, it may also be intersecting with the other curve that we had considered here. So, this is the other, I am sorry, the other curve that we had considered here. So, which point you get, if there are if you are within the range where there are 3 solutions are possible, which point you will get depends on your initial guess and your iterative procedure. So, it will take you to one or the other solutions now. So, it depends on your initial guess, you will get one or the other solution, and if you are within the range which is greater than that V c that I had told before, you may not get any solution at all. So, that is the selective harmonic elimination problem. You can really extend that problem, you can generalize that problem. So, the problem that we had stated here was to solve only these two equations. Instead of V7 you can take V11, you can take V13, any one particular harmonic can be eliminated depending on what you want to be done, that depends on the application. And then if you have more number of switching angles, let us say you have 3 switching angles, it is possible for you to have it as a 3 angle problem now. So, now let me say I have V1 is 1 minus 2 cos alpha 1 plus 2 cos alpha 2 is equal to V1 star. This is my desired voltage. Okay, there is another cos alpha 3 also here. So, I can have V phi is equal to 0 as another equation. This is again 3 switching angles are going to be there. It is going to be 1 minus 2 cos phi alpha 1 plus 2 cos phi alpha 2 or 2 cos 7 alpha 3. Again V7 is equal to 0 can be a third equation. There are 3 angles alpha 1, alpha 2 and alpha 3. So, there are 3 variables, it is possible for you to solve this and come up with this now. In this kind of a situation what you will have is, it may not be in an intersection of 2 different curves. Now, this is alpha 1 and alpha 2, when you are considering only 2 switching angles, you are on a plane. If you are considering alpha 1, alpha 2 and alpha 3, you are in a 3 dimensional space now. So, your desired V1 may not be a curve, it itself will be a surface. And again when you say V7 is equal to 0, you may find multiple surfaces there, like this might become a surface and that might become an equivalent surface. So, you are looking at, and V phi is equal to 0 will be another surface. So, you are looking at the intersections of let us say 3 different surfaces in a 3 dimensional region. So, this idea you can just go about extending. So, it will give you some kind of an idea as to what you can start from now. Many a times you can solve from this point, as I said, that 60, 90 as I said, there is an equivalent point at which there are the waveform is a triplet frequency waveform. It can be a third harmonic or it can be a 9th harmonic or it can be 15th harmonic. You can always come up with some switching angles for any number of switching angles alpha 1, alpha 2, alpha 3 say, it is possible to come up with that. And so, at that particular point you will the waveform could be a 9th harmonic square wave, and at that point, or a third harmonic square wave itself. So, at that point whatever you have for 3 switching angles you will not get a 9th harmonic square wave, but you will get a third harmonic square wave. So, that could be a good point to start your solutions many a times, because that point naturally satisfies Vn is equal to 0 equation now. So, this is, I hope that this has given you some idea of what selective harmonic elimination is. There are several papers and there are books which can give you details of this, and they can also tell you the way the angles alpha 1, alpha 2 etc. vary with the fundamental voltage. Those curves are plotted. So, hence I am not doing it here. So, you find that information here. What I was trying to do here is to get a kind of an insight, to take it limited to 2 switching angles, so that we can deal with it on a plane, on a graph sheet, and get some understanding of this now. So, one of them is to realize that sometimes there could be no solution, there could be multiple solutions, and I hope you did develop some idea about selective harmonic elimination. So, thank you for your interest in this lecture, and I am hoping to see you again in the next lecture. Thank you very much.